Whether you are a practicing scientist or whether you are simply a consumer who is trying to decide which product to buy at the pharmacy, you are going to need to evaluate scientific claims throughout your life. And to help you learn how to do this, we are going to talk about this topic, which I am calling a beginner's guide to evaluating scientific data. Let's jump right in. And this was, I think, a New York Times article, if I recall correctly, entitled "Coca-Cola Funds Scientists Who Shift Blame for Obesity Away from Bad Diets." So why do we need to be cautious about accepting scientific claims? We're going to focus on health claims here. Always remember that a claimant's motivations are not necessarily the same as your own. They might have an interest in the question just like you do, but they might also have other interests. For example, they might want to sell you a drug, a therapy, or a medical device, etc., because they have some interest in it and will receive some money if it sells better. So that's a pretty obvious conflict of interest. However, even authors who are writing articles about scientific claims and don't have any financial interest in the drug, therapy, or device, they might still have an interest in making a claim sound stronger than it is. And this could be because they want to sell you a book or a magazine. For example, weight loss books are a popular topic, and if claims that are being made sound scientific and sound compelling, that author might sell more books. Similarly, anytime you're in the checkout line at the grocery store, you are going to see articles, and I just took prevention as one example, 20 home remedies doctors love. So articles that make scientific claims. And in making those claims, the magazine might have an interest in helping protect your health, but they probably also have an interest in simply selling more magazines. I'm picking here on popular press articles. These are articles written for the general public, not articles written by scientists for scientists. However, even in those articles written by and for scientists, there is a reason that we need to be cautious. This reason is generally referred to as publish or perish. What that means is that academic researchers need to constantly produce new scientific research that makes claims that are interesting enough that some journal will be willing to publish their article. And one way of making an interesting claim is by taking your data, and even if your data doesn't show very much, sort of exaggerating what it shows or being incautious with your claims such that you suggest it shows more than what it really does. And for this reason, even when we are reading scientific articles, we need to be careful about just accepting the claims. And as I said, we're going to focus on health claims here because the health industry is a multi-billion-dollar industry and large amounts of our money are spent on purchasing health-related products. Also, these claims are just very common in our environments, as we saw with the prevention magazine, and so as we go through lives, we experience these daily. But these same principles would apply to other things, even if they are not making health claims. So we're going to move on and look at an example where the researcher's motivations for making a claim are not necessarily those of ours. This headline is from the New York Times in 2015. It says, "Coca-Cola funds scientists who shift blame for obesity away from bad diets." And so this was an article in the newspaper about the fact that Coca-Cola is giving money to scientists who then do studies and publish those studies. The studies show that exercise is more important than diet in determining health. The reason that Coca-Cola benefits from this is clear. If they can convince people that diet isn't important, then maybe people will continue to consume Coke and other sugary soft drinks, for example. The reason this is beneficial to the scientists doing the study is also clear. If they have money to do the studies, then they can maintain their laboratories and they can maintain their positions. And so this is a case where even a practicing scientist writing an article for other scientists, we would want to think about, is their motivation in fact good, and does it agree with ours? Let's look at this in a more quantitative way. This is a table from a meta-analysis. It's a study of studies, and specifically it's looking at the proportion of trials that favor a new treatment over the currently accepted treatment. And so these can be in a couple of different categories. Let's just focus here on drug trials. That's the third row down. And so new drugs are tested to see whether they work better than the drug currently used for some particular ailment. And sometimes these studies are done in not-for-profit settings. So this could be a hospital that is a not-for-profit hospital, or this could be a university laboratory. Sometimes studies are done by for-profit companies. For example, the pharmaceutical company does its own study, and sometimes it's a mix of the two. And so if we focus on this third line down for drugs, what I want you to do is look at the pattern. Does it make a difference of whether the study was done at a not-for-profit hospital or a for-profit one in the outcome of the study? So the first numbers are a fraction. The second number is simply that fraction converted into a proportion. Go ahead and look at that question here before you move on. Hopefully, in looking at the data, the pattern that you noticed is this. If there's a not-for-profit institution doing this study, then only about 40% of new drugs are deemed better than the currently accepted ones. However, if it's a for-profit company doing the study, then about 2/3 of the drugs are in fact shown to be better than the ones currently used. And if it's a mix of profit and not-for-profit, then the proportion is somewhere in between. What does this suggest? This suggests that either for-profit companies are only doing studies of drugs that they know are going to be successful, or that for-profit companies tend to do the studies in a way that is more likely to show the drug being successful than are not-for-profit institutions. That does not necessarily mean that they are making up any data, but they could be making choices in the study design that are going to tend to favor one outcome. If we accept that not-for-profit institutions are only interested in preserving our health, but for-profit ones are interested both in preserving our health and in selling their drug, then we might have some reason to think that the not-for-profit studies are more reliable for our purposes than are the for-profit studies. We're going to move on now and talk about how can we actually evaluate scientific claims. And I'm going to give you a list of 7 questions that you should use when you actually make these evaluations. One of the questions has a couple of subparts. We'll get there for number 3. So the first question we've already talked about. That is, what is the motivation of the claimant? Why are they making the claim? Second is an idea that we talked about earlier in the semester. Is the evidence for the claim based on correlation only, or is there a manipulation that actually shows causation? Third, we want to ask, what is the inference space? In other words, what is the range of population being studied and also the range of treatments that were tested in the study? because we can't really apply results outside of that population or outside of that range of treatment and have a lot of confidence in the outcome. Fourth, it is always important to ask not simply, is there a benefit or a harm, but how large is that benefit or how large is that harm? Fifth, we usually want to know something about the sample size. Were many people or many animals tested, or were there a small number of people or a small number of animals tested in the study? The larger, generally, the more confidence we have. Sixth is the question, are the results statistically significant? So this is equivalent to what we've done looking at graphs and looking at whether error bars between adjacent bars overlap. And if they do overlap, we say the results are not significant. If they don't overlap, we say that they are. This is another way of stating it. We simply want to know, is the effect of the treatment relative to variation within treatment groups large enough that we can rule out chance alone being the cause of the apparent effect? And the last question is a catch-all question. It is simply, are there problems with the logic of the study or with the interpretation of the results that the authors provide that make us doubt whether in fact the study is reliable? We've talked about correlation and causation before. Remember that in a correlation, there's a pattern between two variables. That pattern between variables might suggest a causative relationship. It might suggest that one of the particular variables affects the other one in some specific direction. However, in most cases, it's also possible that the pattern instead results from an unmeasured third variable that affects both of the two that we were measuring. Or it could be that there's only two variables affecting each other, but the one that we think is the dependent variable is actually the one that is the cause, and the one that we're thinking of as the independent variable is actually the one being affected. Because of these potential problems, studies that show correlation only are deemed to be less definitive than a study that involves a manipulation and that is therefore possibly able to show causation. We can contrast correlation studies with manipulative studies. In a manipulative study, then the researchers aren't just looking at natural variations in two variables. Instead, the researcher is controlling the level of one variable and setting it themselves. As a result, if they do find an effect of that independent variable on the dependent variable, then the direction of causation is clear, and this problem that we talked about with correlations would not apply. For this reason, manipulative studies are generally deemed to be stronger than correlational studies. Let's look at an example here. The graph is showing the global average temperature, which is on the y-axis, compared to the number of pirates. And this goes in reverse order from many pirates here down to fewer and fewer pirates at this end of the scale. And what I want you to do is look at the relationship. As the number of pirates has decreased from about 35,000 down to about 17, the global average temperature has increased by nearly, well, 1.5 degrees or 2 degrees Celsius. So the question here is, does this actually show that the number of pirates affects the global average temperature? Think about that for a second, and then we'll talk about it. Hopefully what you concluded is, of course, no. The number of pirates does not affect temperature, and temperature probably does not affect the number of pirates. Instead, there's a third variable we're not thinking of, which in this case is simply time. Over the last couple of centuries, I'm guessing, the number of pirates has decreased substantially. And over the last century, the global average temperature has gone up by 1.5 degrees Celsius. As a result, there's a pattern between the two variables that has nothing to do with one of them affecting the other. So that's a silly example of correlation or causation, but we will also look at other examples where it is a little bit less obvious and maybe more important. We're going to move on now and talk about inference space. And as I said, for inference space, there's actually two sub-questions. The first one is, what is the population being studied? Now note, this is not the sample size. That will come up later. This is instead characteristics of the population. Examples of population characteristics that might be relevant in a human trial would be the age of the participants. If, for example, a study is done showing that a particular drug lowers blood pressure, and the study is done in 30 and 40-year-olds, it might not apply very well to teenagers, and it might not apply very well to 70-year-olds or 80-year-olds. Similarly, we might want to think about sex. A study done on all males might have results that apply poorly to females. We might want to think about race. Different populations with different genetic makeups, as well as different environments, can respond differently to different treatments, for example. And you could make a more complete list thinking about things like income and access to health care, current health status, accessibility to health care, and topics like that. Even more basically, in many studies that are related to medicine, we need to ask, is the study being done on humans, which are usually the organisms we are interested in, or are they being done on mice, or rats, or flies, or some other kind of organism? Again, if a study is done on humans, then we can probably extrapolate the result to other humans. But if it's being done on mice or rats, then it is less obvious whether those same results would apply to humans. So here's an example. This is a summary of a study that was published last year in the Proceedings of the Mayo Clinic, and here's the author. And in summary, what they found, or at least part of what they found, was that physically active white men are at high risk for plaque buildup in arteries. So the study showed specifically that among people who are very active, that there's a risk for calcium buildup in arteries, which is CAC, coronary artery calcification, and that this risk is particularly strong for white males. In fact, for white males, they found an odds ratio of 1.8, meaning that at these high exercise levels, the participants or the study members were almost twice as likely, 1.8 times as likely of having these buildups as were males who weren't in this group. They noticed similar trends, but they weren't as strong for white females. And when they looked at black participants, there was not any trend towards coronary artery calcification. And so there seems to be a difference in this variable depending on the participant's race. Here is why this finding is so important. It suggests that exercising at long and strenuous endurance levels can lead to buildup of calcium arteries, or calcium in coronary arteries, which is a bad thing. And if the study was only done on white male participants, then we wouldn't know that this risk was really strongest for that group, and lighter or perhaps non-existent for other groups. For various reasons, many medical studies are done on men and are not done on women, and they're also typically done on middle-aged males rather than children and rather than the elderly. The problem with this is that it then means that we know less about how different medical interventions can affect other groups besides middle-aged males. Let's move on to the second part of inference space. And this is a focus instead of on who's being tested, it's a focus on what is the range of treatments being studied. The reason this is important is that the relationship between a different level of a treatment and the effect is usually nonlinear. So if having one dose of something is a good thing, that does not necessarily mean that 2 doses is twice as good and 10 doses is 10 times better. For example, if we think about the benefit or harm of too much coffee, just because that's one of my favorite examples, you could imagine that having a little bit of coffee is pretty good for your well-being, but there's some point where you have so much coffee that the benefit starts to go away, and there can be a point even beyond that where if you continue having more and more coffee, then instead of a benefit, you're actually getting a harm, and that harm gets greater and greater and greater, and there should be some amount of coffee that is actually toxic to the body. So let's imagine any particular study. A study will not necessarily look at this whole range of dosages. So there might be a study of caffeine consumption that looks at whether you have better health if you drink 1, 2, or 3 cups of coffee a day. And that study would only be focusing on this part of the graph. If we use those results to make inferences about what would happen for somebody who is drinking 10 or 15 cups of coffee a day, they're way out here on the graph, but we wouldn't know anything about the shape after this point at our 3rd cup of coffee. So we might think this line just continues to go up and up and up. Similarly, if we looked at a study that focused only on people who have between 10 and 20 cups of coffee per day, just to make up some numbers here, we would see that coffee causes increasing harm. And that also doesn't tell the full story. It would be relevant between the range of 10 and 20 cups of coffee a day, but it wouldn't tell us anything about the great benefits of having between 0 and 5 cups of coffee a day, because that wouldn't have been part of the data collected. Of course, I'm making up the coffee example here, but you can imagine similar trends for real-life examples. We will move on to our next question here, and that is, how large is the effect? This is probably the most common problem with popular press articles written not for scientists, but for the general public, in how they present findings. The articles are usually good about telling you whether the particular treatment increased or decreased some variable, but they're usually really bad at telling you whether the effect is large or small. To really understand how large an effect is, we need to know a couple of things. First, we need to know what the baseline measurement is without the treatment. In other words, we need to know what the dependent variable is for our control group who's not receiving any treatment. We then need to know how much our dependent variable changes when treatments are applied at levels that are relevant to what we're thinking about. This is more easy to think about with an example. So let's look at an example here. What we're looking at, I'm just going to simplify, is the odds ratio for getting a particular kind of brain cancer depending on the hours that the person has talked on their cell phone over the past 1 to 4 years. And so we can see different categories here. And some people talked on their phone for less than 5 hours over the last 4 years. Some people talked between 5 and 115 hours, 115 to 400 hours, and you get the idea. This last bar is people who talked on their phone over 1,640 hours in the last 4 years. So those are the 5 different bars. What we have on the y-axis is the odds ratio for getting brain cancer. This blue line equals 1, which means you are no more likely or less likely to get brain cancer than somebody else. Anything below this line means you are less likely to get brain cancer. Anything above this line means you are more likely to get brain cancer. So according to this graph, it looks like talking on your cell phone a lot, about 400 hours per year or more, dramatically increases your risk of getting brain cancer. In fact, it goes up more than 4-fold, suggesting that you'd have more than 4 times the likelihood of getting brain cancer as somebody who is talking not at all or less than 1,600 hours over those years. That's the pattern. Now we should talk about whether this is really telling us the size of the effect. In a way it is, but in an important way it's also not. And the reason for this is that there's some important information missing. That is the baseline rate of getting brain cancer. This is kind of equivalent to our negative control. For somebody who's not exposed to cell phones at all, their risk of getting brain cancer is about 1 per 10,000. What does this mean? This means that this 4-fold increase in risk of getting brain cancer is really just an increase in 1 per 10,000 up to 4 per 10,000. So is that a big increase? Well, it is still 4-fold, but is that something that would concern you as a person trying to decide whether or not to talk on their cell phone? Going from having a 1 in 10,000 to a 4 in 10,000 risk of getting brain cancer? There's not a right answer to that question, but for most people I'm guessing the answer is no. They would not especially care about that increase in risk, because even going up to 4 in 10,000, it is still an extremely low risk relative to other risks in our lives. And so what I want you to get from this is that when we say it's important to say the direction of effects and the size of the effect, the size should not just be expressed as a fraction of the original, but we also need to know something about the actual value of the original. Let's imagine, just for the sake of an example, that the risk of getting brain cancer in the US was actually more like 1 in 100. If that were the case, and talking on your cell phone a lot led to a 4-fold increase in your risk, then we'd be talking about going from a 1% to a 4% risk, and that is something that might be big enough that it would start to scare a lot of people. So knowing that baseline is really important. Before we move on from this example, I do want to say that this study had some other problems. The problem of the risk of brain cancer being low wasn't really one of them. The real problems with this study have to do with these numbers being what people remember after they've been diagnosed with brain cancer or not. And so these numbers aren't necessarily all that reliable. So I would not use this as evidence that you need to worry about talking on your cell phone and getting brain cancer. But because of this increase, it still seemed like a worthwhile example to talk about. The next question we have to ask is how large of a population was tested? So to use a hypothetical caffeine example again, this shows different exposure to caffeine during the day going from none up to a moderate amount, and then the score on memory tests. And we can see that there's a positive slope here. So as people have more caffeine, they tend to do better on the memory tests. However, you can also see that in this hypothetical study, only about 8 people were tested. That means that we probably don't have a lot of confidence in the results. If this one person had happened to perform badly, and the data point was down here, then our entire best fit line, or this line that goes as close to all of the points as possible, would switch to going downwards instead of upwards. So whenever any one data point has a big effect on a line like this, it's a good sign that we need to be cautious. Now let's imagine the same study, but done with 100 or so people instead of just about 8 people. In this case, even if we found a line that had the same slope as the line in our other example, we would have a lot more confidence it was true, because with 100 data points influencing where this line lays, then if any one of those data points gets moved, that does not actually substantially change the slope of this line, because no one of these data points has a large effect on its own. Therefore, the larger the study is, the more individuals that are tested, the more confidence we tend to have in that study. The final question that we need to ask is, are the results statistically significant? This is really a way of saying, can we reasonably rule out the likelihood that the results could have arisen by chance alone? We don't want chance to be the cause of the results if we want to trust the results. We want to be able to rule this out. If we can, then we are able to say that something else was likely the cause. So if chance was not the cause, then the other possibility is the effect large enough relative to variation within groups that chance is unlikely to explain the results? This is equivalent on our bar graphs that we've looked at to asking whether the error bars overlap or do not overlap. If they do overlap, then we can't rule out the possibility that chance caused the results. If they do not overlap, then we can say that the variation is large enough relative to variation within groups that we can reasonably rule out chance as the explanation. In scientific papers, this is sometimes shown graphically with error bars, but there will also be values reported called p-values. A p-value is the same thing as the significance. And for p-values, we always want lower numbers. So the lower the number, then the less likely it is that chance alone explains the pattern. The cutoff value that we typically use for this is p less than 0.05. That's the same thing as 1 out of 20. And really what this number, p equals 0.05, is telling us is that if chance alone were the only thing affecting results, we would only find a pattern this strong or stronger less than 1 out of 20 times. If that would only happen less than 1 out of 20 times, then it is unlikely. If it would happen more than 1 out of 20 times, then we might not be confident enough in ruling out chance that we're willing to accept that the independent variable actually affected the dependent variable. So in studies that you read by scientists for other scientists, you'll typically see the p-values actually listed in a numerical form. If you are reading a popular press article written for the general public, then for the author to address this question, the most likely thing that you would see is the term statistically significant. Now, many authors of popular press articles leave this term out, even if the results are statistically significant. So while this is a good thing to put in, its absence in the popular press article doesn't necessarily mean that the results in the real study weren't significant. It might just be that the author of the popular press article didn't think it was important to say this. They just assumed it. So here's a review list of the 7 questions that you need to know to ask. And you should memorize these so you'll be familiar with them on the next exam when you need to evaluate an article. Again, the first question is, what is the motivation of the person making the claim? The second question, is the evidence based on correlation or on a manipulative study that can show causation? Third, what is the inference space? And we talked about 2 portions of that. One relates to the population, and one relates to the range of treatments. Fourth, how large is the effect, and what is the baseline number that we are comparing to? Fifth, what is the population size? Sixth, is the effect statistically significant? And then we're going to also add a catch-all question to the end of the list. Are there any problems with the logic of the study, or how it was performed, or how the results were interpreted by the authors that make you doubt what they claim, even if it's not for one of these reasons mentioned earlier? When you answer this question on an exam, you should not talk about these other things that are already talked about in a different question. This question is exclusively reserved for problems that you see that did not come up in one of the earlier categories. And some final thoughts. First, these questions are a guide only. This is not a complete and exhaustive list to critically evaluating the scientific literature. And we don't necessarily need to completely reject studies or reject articles that fail to address one or more of those questions. There might be still valuable information in the article, but you need to be aware of the limitations when you are making your interpretations and evaluating your confidence. And finally, kind of like question number 7, studies can be limited in all sorts of ways, only some of which are on that list that we just talked about. So whenever you are reading a scientific article, you need to think about what are the strengths of the study as well as what are its limitations.